Our next speaker, Dr. Serhat Hosder, is also virtual, so I will begin introducing him while we switch over to his set of slides. Dr. Serhat Hosder is currently the James A. Drallmeier Centennial Professor of Aerospace Engineering in the Mechanical and Aerospace Engineering Department at Missouri S&T and serves as the Director of Aerospace Simulations of the Aerospace Simulations Laboratory. He received his PhD degree in aerospace engineering from Virginia Tech in 2004. Professor Hosder's research activities focus on the fields of computational aerothermodynamics, multi-fidelity modeling and uncertainty quantification of hypersonic flows and technologies, directed energy for hypersonic applications, planetary entry, descent, and landing of spacecraft, and aerodynamic shape optimization. His recent research projects have been funded by the DoD Joint Hypersonics Transition Office, NASA, the Missile Defense Agency, National Science Foundation, and industry. Professor Hosder is a Fellow of the Royal Aeronautical Society and Associate Fellow of AIAA. He was the past chair of the AIAA Hypersonic Technologies and Spaceplanes Technical Committee between 2019 and 2021, and currently serves in the steering committee of that same technical committee. Today, he will be presenting a topic entitled Towards Flight Uncertainty Prediction of Hypersonic Entry Systems. Over to you, Dr. Hosder.
Thank you for the invitation. Today, I am going to be talking about our efforts towards flight uncertainty prediction of hypersonic entry systems, specifically focusing on the uncertainty quantification for model input related uncertainties. So here I would like to start with the outline of my talk. First, I'm going to give the motivation for uncertain quantification, then briefly describe the flight uncertainty prediction approach, and then focus mostly on the model uncertainty quantification approach that we have been using for various hypersonic problems, including the entry technologies. And after giving the description of the approach, I am going to present two application problems. One is going to be a stagnation point heat flux prediction of a hypersonic vehicle with a reduced order correlation, a model problem, mainly to validate our approach. And then I am going to present some results from a large-scale problem, which will be the thermal protection system, or in short, TPS, response of a hypersonic inflatable aerodynamic decelerator. And then I will conclude my talk. So we rely heavily on modeling and simulation for the development of entry technologies, the entry capsules, due to the limited ground testing data and the flight testing data. And we use modeling and simulation mainly to simulate this extreme environment, hypersonic environment, the high temperature environment around the vehicle. And as you see here, we have complex physics associated with the flow field, the surface, and then the coupling between the flow field and the surface. We have strong shocks, high temperature flow field, which may include chemical reactions, interaction with the surface, ablation, and turbulence. And in addition to the inherent uncertainties related to the environment, we also have significant uncertainties in the physical models. So we have a number of reasons to include the uncertainty quantification in modeling and simulation. And one obvious reason is to improve the prediction accuracy of our models. And here you see that by using uncertainty quantification and by a byproduct of uncertainty quantification is sensitivity analysis, we can identify important significant uncertainty sources in our model. And then we try to plan our ground and flight testing to reduce these errors. In turn, we try to improve our prediction accuracy. And then the other motivation to include uncertainty quantification is to evaluate the flight performance under uncertain operating conditions and model uncertainties. And then we can also utilize the modeling with uncertain quantification in the flight qualification of entry systems. We can calculate the uncertainties and the margins, and then using the quantification of margins and uncertainties methodology, we can try to certify our systems. And finally, we can integrate the uncertain quantification to the design of the vehicle to increase the robustness and the survivability. With this, we are reducing the impact of the uncertainties on the vehicle performance and the reliability. So here, I would like to give a brief description of our approach for flight uncertainty prediction with the computational models that we use. Here you see the computational model. It's a CFD model. We simulate the hypersonic environment or a hypersonic inflatable aerodynamic decelerator. I included it as an example. And then in our approach, we also utilize available ground test data and also the flight test data, because our objective is to get the total uncertainty in the predictions to be able to predict the uncertainties in the actual flight. So I'm going to start with the uncertainties associated with the computational model. We have what we call model input uncertainties, which could be, as you see, the probabilistic, or they can be non-probabilistic, epistemic uncertain variables. Any uncertainty that we don't have enough data, for which we don't have enough data, we can also treat them as epistemic uncertainties. And in our approach, for non-probabilistic or epistemic uncertainties, we typically use interval approach. So we have a mixed uncertainty set, and we propagate this through our model, and that's what I'm going to be focusing on the rest of this talk. And then this gives us the model input uncertainty for our response to quantity of interest, which could be a surface pressure, shear, heat flux, the recession rate due to ablation. And just to give you some idea, these uncertainties may include sources coming from operating conditions, the uncertainty in the vehicle shape, the change, the modeling parameters in chemical kinetics, turbulence models, the ablation, and radiation. Since we are solving our problem numerically, we also need to include the uncertainty coming from the numerics, such as the discretization error or iterative convergence error. And then we have to compare the model input uncertainty appended with the numerical uncertainty to the actual reality. And then we will be comparing our results to the experimental data or the flight test data. And the way we compare our simulations to this experimental data is done through validation matrix, which gives us the model form uncertainty. So overall, when we add all these uncertainties, we have the total flight prediction uncertainty with our computational model. So now next, I am going to be focusing on the model input uncertainty quantification. And I'm going to start first with challenges for the aerothermal uncertainty quantification. As I described, we are dealing with a very complex multidisciplinary physics problem. So our simulation codes are very expensive to evaluate. So, and then we typically need to do high fidelity simulations, and we cannot afford a typical Monte Carlo simulation to propagate our uncertainties because it's going to be too expensive and not feasible. And we are addressing this challenge by utilizing stochastic surrogates based on polynomial chaos theory, which I'm going to talk next in my slide. Another challenge is that we need a non-intrusive approach so that the computational models, such as our CFD code, require no major modification. So we use legacy codes. We have our own codes, which are thousands of lines, and we do not want to rewrite them. We want to use them as a black box as much as possible. And for that, we are utilizing non-intrusive polynomial chaos, which will mainly use the deterministic simulations as samples obtained from this simulation codes. And also, as you can imagine, since we have a complex problem with multidisciplinary, also having a multidisciplinary aspect, we have a large number of uncertain variables. And this becomes a challenge. Even if you use this NIPC approach, it becomes a challenge. To address this, we've been utilizing nonlinear sensitivity analysis, global nonlinear sensitivity analysis done with Sobel indices, which can be obtained from our polynomial chaos expansions for dimension reduction. And in addition to that, we are using a sparse sampling approach for our NIPC to be able to efficiently propagate our uncertainties when we have a large number of input uncertain variables. Finally, as I described in the previous slide, we have mixed uncertainties for our model input, both inherent and epistemic. And to be able to propagate this mixed uncertainty, we are using nested uncertain propagation or second-order probability. And then we are replacing the deterministic code with our surrogates obtained from the polynomial chaos. Now, I would like to talk about our sensitivity and uncertain quantification approach, which is based on the polynomial chaos theory. In this, we represent our uncertain response. It could be heat flux, pressure, or another quantity of interest in terms of a surrogate model, as you see here, a polynomial expansion. And this expansion has, in theory, infinite number of terms, but for practical applications, we truncate the number of terms, which depends on the number of variables and the degree of the polynomial we use. Each term in this polynomial expansion has this deterministic component. And then we have this random basis functions, which are orthogonal polynomials. Now, there are different ways of obtaining these coefficients, which are the unknowns in our expansion. For our problems, for hypersonic entry problems, we've been mostly using this point collocation and IPC approach, where we produce a number of samples and evaluate this model at those sample locations, which gives us this linear set. And this is the number of samples we use. And here, NT is the total number of output modes, which is going to be a function of the number of uncertain variables and the polynomial order of the total expansion. Now, depending on the number of samples, we can have different approaches to solve this linear set. When we have our number of samples is equals to NT, we have mainly the required number to obtain a solution with the determined system. When the number of samples, we can always take more samples than the required, then we have an overdetermined system. We can define an oversampling ratio, and we had problems where we used an oversampling ratio of 2, which worked fine. And then in this case, we obtain our solution through least squares approach. But for these two cases, even though we use a polynomial calculus approach, when we have a large number of uncertain variables, again, the required number of simulations can be very high. So in order to address this problem, we've been taking less number of samples than the minimum required, which gives us an underdetermined system for that linear set. And this is actually the basis of our sparse sampling approach. It is going to be the most efficient approach in terms of the computational cost. With this approach, since we don't have a unique solution, we try to find the solution with the fewest number of non-zero coefficients in our expansion. Each coefficient, the terms, you remember, have a coefficient, and the terms that do not contribute to the uncertainty much, they're going to have very small values. So with this approach, we force them to be equal to 0, and we achieve that through an L1 minimization problem here. And this is an iterative approach. We start with a certain sample size, and then we add more samples. So it's an incremental approach. And we check the convergence of our expansion, the coefficients, by calculating the total Sobol indices of all the variables and then averaging it. And once we see that there is no change in that error, then we determine the convergence. Now, the other component of our uncertainty approach is to propagate the mixed uncertainty. As I mentioned, we use a nested approach, which has an inner loop for the inherent uncertainties and an outer loop for the epistemic uncertainties. So for a fixed value of the epistemic variable, when we perform the inner loop, we get a CDF, and when we repeat it for all the epistemic variable, the range, then we get a probability box, as you see. And then we can utilize this probability box to get some different statistics. For example, here you see how we calculate the 95% confidence interval by using the bounding CDFs. And in this case, the efficiency comes from the fact that we're not using the original simulation code, but we replace it with our surrogate model obtained with the NIPC. Now, I'm going to present our first application problem. This is a model problem, a validation problem to predict the stagnation point heat flux on a blunt entry body. And this is a correlation, so it is cheap to evaluate, and we can do Monte Carlo with this model so that we can compare our approach to the Monte Carlo results. Of course, I'm not going to go in detail over this. This is our mathematical model. So for this case, we considered 11 uncertain variables. 7 of them are epistemic uncertain variables, as you see, and then we have 4 aleatory or inherent uncertain variables. And then with 11 uncertain variables, if you use a second degree polynomial expansion, then the minimum number required is going to be 78. We solved this problem with the sparse sampling approach using different samples, increasing it iteratively. And then we compared our results to a Monte Carlo simulation with 400,000 samples, and then an IPC expansion with an oversampling ratio of 2, which required 156 samples. As you see in this probability box plot, as we approach to, or once we reach to 50 samples, we have a very good agreement with the Monte Carlo and our NIPC obtained with oversampling ratio of 2. And here you see the convergence around 50 samples, like we reduce our error by 3 orders of magnitude. And once we have a converged solution, then we can look at the Sobol index ranking. Here we see the largest Sobol indexes for the free stream and then the Prandtl number. So as you see, by incorporating Sobol index, both checking the convergence of the sparse sampling approach, we also use the final converged values in ranking the significant uncertain sources. Next, I'm going to present a more complex problem focusing on hypersonic inflatable aerodynamic decelerator concept, HyTASP. This concept is primarily being developed to address increased capability needed for landing higher mass at higher altitudes on Mars and eventually to use for human missions. And as you see, you can stow this packet in a launch vehicle. And then before the vehicle enters the atmosphere, you can inflate this structure. And the structure has a flexible thermal protection system. So we worked this as part of an NASA project, and it's a multidisciplinary problem. Therefore, even though our eventual goal is to predict the uncertainty in the thermal response of the flexible TPS, we need to still consider the uncertainties in the hypersonic flow field modeling because it affects the thermal response. And also we had to do consider the uncertainty coming from the structural modeling. And I use those in the prediction of the uncertainty in the flexible TPS modeling, which I will describe next. And we consider uncertainties in the operating conditions and also various uncertainties in the physical models related to the flow field, the TPS, and the structural modeling. So for this problem, we are considering a 10-meter diameter height for a nominal ballistic Mars entry. And then first, we would like to identify significant uncertainty sources in the flow field, which affects the aerodynamic heating, shear, and pressure, and then use them in the uncertainty quantification of the flexible thermal protection system response. And here you see a simplified layout of the flexible TPS. It is made up of different layers. You have outer fabric layer. It's a silicon carbon-based fabric. Then you have some insulation layers. And then you have this final layer between the gas barrier at the TC6 location. And that is the location that we are interested in, quantifying the uncertainty on the temperature at that location, which is the bone line temperature. So here, quickly, we are using high-fidelity CFD code from NASA, LoRa, modeling the flow field. And then also we have a thermal response model coupled to the CFD solution. And these simulations are also expensive. That's why we are using the sparse sampling approach. So here, just briefly show the baseline results with new uncertainty. So if you look at these 3 points over the flank region of the HyTASP, you'll see that when we solve the deterministic problem, you can get the history of the temperature at this T6 location, the bone line temperature as a function of time. And then here, if we just focus on point 2, we can also look at the temperature history of, at different point locations, in-depth locations at that point, TC1 to TC6. And one thing that to see here is we do not want the temperature to exceed 400 degrees Celsius at this TC6 location, the bone line temperature. And at 70 seconds, the HyTASP separation occur. And here we have the uncertainty sources considered in our analysis. We have uncertainties coming from the flow field analysis, which affect the aerodynamic heating and the surface pressure. We have this reduced set, which are obtained from the sensitivity analysis of the hypersonic flow field. Originally, we had 59 variables, and we were able to reduce it to 4. In addition to aerodynamic uncertainties, we also have a number of uncertainty sources related to the thermomechanical properties of different layers of the flexible TPS. And in total, we have 22 uncertain sources, and some of them are here, as you see, inherent aleatory, and the others are epistemic. So here, I would like to present the results from our uncertainty analysis at that PT location, focusing on the bone line temperature. You see that we have the nominal temperature distribution with the black curve, and then you here see the 95% confidence interval marked with this gray zone, bounded by these red dashed lines. And if you look at this plot, we see after the 40 seconds, we see a significant increase in the temperature and the associated uncertainty. And in fact, at 65 seconds, our upper bound for the 95% confidence interval exceeds the 400 degrees Celsius, that critical temperature. Now, when we look at what causes this increase in the temperature or the dominant sources contributing to the uncertainty, we can plot the Sobol index as a function of time at this location for each variable. Here I'm showing the top 8 uncertain variables. And if you look at the 70 seconds, we can see that the dominant uncertainty is the number one uncertainty is the thermal conductivity of the outer fabric, followed by the thermal conductivity of the first inner layer, and then the third important parameter here is the density, the free stream density. So with this, I'm going to conclude my talk. I briefly outlined a framework for flight uncertainty prediction of hypersonic entry vehicles, described an efficient aerothermal uncertainty quantification approach with stochastic expansions, demonstrated the uncertainty quantification approach on thermal protection system response of an HyTASP for Mars entry. And I would like to add that integrating uncertain quantification to entry vehicle development, such as the new technologies like HyTASP, early in the design process is also important for timely changes in vehicle configuration, TPS selection, sizing, increasing the robustness, and resource allocation for ground and flight testing. And here I listed the references if anyone wants to learn more about our approach. Thank you.
Thank you, Dr. Hosder. Anyone have any questions?
Hello. I believe it was back on slide 6 where you were showing how to solve or choose a solution to an equation that didn't have a unique solution with the number of parameters that were not equal to 0. You chose the solution that had the fewest parameters equal to 0. I was wondering why that might be preferable to what might seem like the parsimonious solution that has the most parameters set equal to 0.
I think it's fewest number of non-zero coefficients. So we are trying to increase the number of coefficients which are equal to 0.
Oh, okay. I misheard. Thank you.
Yeah. Just here it's non-zero. So again, each coefficient you can think about as, if the coefficient is large, you will have a larger contribution to the overall uncertainty. So it's almost like a sensitivity analysis. So if I have very small values, then I try to force them 0 to retain only the important terms in my expansion.